You are on the fastest train ever built. It travels at 90% of the speed of light. Inside the car, you point a flashlight forward and turn it on. Your common sense, the logic that guides your life every day, says that the speed of the light from the flashlight should be added to the speed of the train. That beam of light should travel faster than light itself. But that doesn't happen. You measure the speed of the light coming out of the flashlight, and it remains exactly the same. 300 million meters per second, not a single meter more. Intrigued, you accelerate the train to 99% of the speed of light, almost at the limit of the universe. You turn on the flashlight again. You measure the same speed, exactly the same. You accelerate to 99.9999%. The absolute limit, you turn it on, you measure it the same, always the same. This break in logic was the starting point for a deep analysis. We used an advanced artificial intelligence system called Numa to investigate a simple question. Why does reality work this way? Because no matter how fast you go, light always travels at the same speed relative to you. This violates everything we've learned about movement, and yet it is a fact measured and proven thousands of times. When Albert Einstein finally understood what this meant, he discovered something that should keep you up at night. Time is not what you think. Space is not what you believe. And there is a fundamental limit in the universe that cannot be crossed, not for lack of technology or energy, but because crossing it would mean breaking causality itself. The logic that a cause always comes before the effect. Asking what is faster than light is like asking what exists north of the North Pole. The question seems to make sense, but it points to a place that doesn't exist. To understand how we reach this conclusion, the analysis took us to the past. We need to go back to the origin, to the story of a man looking at the moon. Isaac Newton had a question that seemed simple, but no one before him had answered correctly. Why do things fall? Everyone knew that things fell. Galileo had already measured this with precision. A free-falling object travels about 5 meters in the first second. But Newton looked up, saw the moon, and asked the question that would change science forever. And the moon, why doesn't it fall? Think about it. The moon is up there, revolving around the Earth. But if it was stationary in space, without any movement, gravity would pull it directly toward us. It would fall and crash into the Earth. It turns out the moon isn't stationary. It moves sideways at an immense speed. And because it moves sideways at the same time that gravity pulls it down, it is constantly missing the target. The moon is, at this very moment, falling toward the Earth. It has been falling for billions of years, but it never hits us. An orbit is exactly that, a state of perpetual free fall, where you move sideways so fast that the ground curves away from you at the same rate you fall. Newton had a brilliant idea and did the math. The moon is 60 times farther from the center of the Earth than we are on the surface. He imagined that the force of gravity might get weaker with distance. If you move twice as far away, gravity becomes 4 times weaker. If you move 3 times farther, it becomes 9 times weaker. Following this logic, at the moon's distance, gravity should be 60 squared, or 3,600 times weaker than here on the surface. If things here fall 5 meters in the first second, the moon should fall 5 meters divided by 3,600. That's about 1.4 millimeters. So, Newton calculated how much the moon actually falls in its orbit every second, using real data of its speed and distance, and the result matched perfectly. The same force that makes an apple fall from a tree is what keeps the moon tethered to the Earth. In that instant, heaven and earth were united by a single equation. For the first time, someone proved that the laws governing our everyday world are the same ones governing the cosmos. This single idea opened the doors to the universe. Suddenly, everything started to make sense. Why do planets move in ellipses? as Johannes Kepler had observed. Because of Newton's gravity. Why are there two tides a day? Because the moon pulls the water on the near side with more force and the earth on the far side with less force, creating two bulges of water. Why are planets and stars round? Because gravity pulls all their matter toward the center. But every theory must pass the most rigorous test of all, time. And it was while observing a very distant gas giant that the first crack appeared. Astronomers used Newton's laws to precisely predict the movements of Jupiter's four largest moons: Io, Europa, Ganymede, and Callisto. And something didn't add up. Sometimes the moons seemed to move ahead in their orbits. Other times they fell behind by up to 8 minutes. 8 minutes is an eternity in astronomy. Something was wrong. Was Newton's law, which worked so well for everything, failing at Jupiter? Or was there something else happening, something fundamental about the universe that we hadn't noticed yet? Most scientists at the time would have concluded that Newton's law needed adjustments, that perhaps it wasn't as universal as thought. But a Danish astronomer named Ole Rømer had an idea that required immense confidence in Newton's mathematics. Instead of doubting the law, he doubted something everyone considered obvious. He thought, what if the law is correct, but our observation is delayed? What if the light we see from Jupiter's moons doesn't show how they are now, but how they were a few minutes ago, the time it took for the light to travel to us? This idea, which seems basic today, was revolutionary in the 17th century. Most people assumed light was instantaneous. Rømer was proposing that light has a finite speed and that this speed could be measured. He noticed a clear pattern in the data. The moons seemed ahead when Earth in its orbit was closer to Jupiter and seemed behind when Earth was on the other side of the Sun, farther from Jupiter. Rømer analyzed the astronomical records from that time and confirmed the pattern Rømer noticed. The delay of the moons was perfectly correlated with Earth's orbital distance. Those 8 minutes of difference weren't an error in the moon's orbits. They were the extra time it took for light to cross the diameter of Earth's orbit. With this, Rømer not only saved Newton's theory, but also made the first estimate of the speed of light. I want you to understand what happened here. The speed of light was discovered not by a direct experiment, but by trusting a physical law that seemed to be failing. This is how science advances. Each discovery opens the door to the next. Newton gave us gravity. Rømer, trusting Newton, gave us the speed of light. And this discovery would lead us to a place no one could have imagined. This is where things start to get really strange. Once you know that light has a speed and can measure it precisely, a bizarre pattern emerges. Light always travels at the same speed. Always. It doesn't matter who emits it, how it's emitted, or how fast the measurer is moving. In our daily lives, speeds add up. If you are on a train at 80 km/h and walk forward at 5 km/h, your speed relative to the ground is 85. Simple and logical. If you throw a ball from a moving car, the car's speed is added to the ball's. But light ignores this rule. You are standing still and turn on a flashlight. The light leaves at 300 million meters per second. Now you get into that impossible ship, traveling at half the speed of light. You turn on the same flashlight. Logic says the light should come out at 1.5 times the speed of light, but you measure it, and it stays at 300 million ms. Exactly the same. This makes no sense at all. It's like running toward a wall, and no matter how much you run, the distance to it never decreases. It was this paradox that kept a young Albert Einstein awake for nights on end. He realized that if the measurements were correct and the speed of light was the only thing in the universe that didn't change, then everything else had to be flexible. Time and space are not fixed. They bend, stretch, and compress. And they do this in the exact way necessary to ensure the speed of light is always the same for everyone. Let me put it another way. The universe adjusts reality to protect this constant. It's not that light is special, it's that the fabric of the universe is built around this speed. When you move fast through space, time passes more slowly for you. Your clock literally marks the seconds more slowly. It's not a defect of the clock. It is time itself slowing down for you. At the same time, the space ahead of you contracts, distances shorten. These effects are not an illusion. They are real and have been measured. Time really dilates, space really contracts, and the exact amount of this deformation is precisely what is needed, so that no matter how fast you go, when measuring the speed of light from a flashlight, the result is always the same. This leads us back to the fundamental question: if time and space can deform to keep the speed of light constant, why can't we just push through and overtake it? Because that is the absolute limit. The analysis revealed that the answer doesn't lie in engineering more powerful engines. The barrier is much deeper. Trying to go faster than light is the same as trying to travel to the past. And that, the fundamental structure of the universe, seems not to allow. To understand why we can't go faster than light, we need to change how we think about movement. You aren't just moving through space, you are always moving through a single entity called space-time. And you do this at a constant speed, the speed of light. Even now, sitting and still, you're traveling through space-time at maximum speed. The point is that this total speed is divided between two directions, space and time. If you are completely stationary in space, all of your movement is dedicated to the dimension of time. You are aging at the maximum possible speed, 1 second per second. But the moment you start moving through space, whether walking or driving a car, you need to steal a bit of the speed you were using to move through time. It is a fixed budget of movement. If you spend more moving through space, there is less left to move through time. That's why the faster you travel in space, the slower you travel in time. And if you could reach the speed of light in space, nothing would be left of your movement budget for time. Time would stop completely for you. That is why light photons do not age. From the perspective of a photon, it is emitted and absorbed at the same instant. Billions of years can pass in the universe, but for the photon, no time has passed at all. It exists simultaneously at its point of origin and its destination. Going faster than light would mean having negative movement in time. It would mean going back to the past. And the universe, in its fundamental structure, protects causality, the rule that the effect cannot come before the cause. But there is another, more practical barrier. As you accelerate any object with mass, something strange happens. It becomes increasingly difficult to accelerate. It's not that it lacks fuel or that the engine is weak. It is the object itself that resists the change in speed more and more. Its inertia increases. Imagine you are pushing an empty grocery cart. It's easy. Now imagine that with every meter you push it, it gets a little heavier. In the beginning, the difference is small, but you keep pushing and it gets heavier and heavier, until it becomes so massive that no force in the universe can move it a single millimeter more. This is what happens when something with mass approaches the speed of light. Its inertia tends toward infinity. To actually reach the speed of light, infinite energy would be required, and that is impossible. Therefore, nothing with mass, not you, not a ship, not a single atom, can reach that speed. It is not an arbitrary rule. It is a consequence of the very structure of space-time. All of this might sound like abstract theory, but it is a reality measured and applied every day. Numa cross-referenced data from technologies we use without even realizing it. Global Positioning System satellites, for example, need to constantly correct for time dilation. They move very fast in orbit, so time for them passes a little slower than for us on the surface. If engineers didn't make this adjustment based on Einstein's relativity, the satellites would miss their location by several kilometers in a single day. Every time you use the map on your phone, you are trusting that Einstein's theory is correct. And there is an even more impressive proof. When cosmic rays hit the upper atmosphere, they create unstable particles called muons. These muons have an extremely short lifespan, only a few millionths of a second. Even traveling near the speed of light, they shouldn't have enough time to cross the atmosphere and reach the ground before disintegrating. They should disappear much sooner, yet we detect them here on the surface. Thousands of them pass through your body every minute. They manage to make this impossible journey because, by traveling so fast, time for them dilates. From our point of view, their life is stretched. From their perspective, the distance to travel has been shortened. Either way they arrive, every muon that hits the ground is living proof that time is not absolute. If time can stretch for subatomic particles, what happens when we apply this same logic to something more familiar, like human life? The answer leads us to one of the most famous and disturbing thought experiments in physics. The idea that time passes differently for different people isn't a metaphor. It's literal physics, and was proven in a real experiment. In 1971, two physicists named Hafele and Keating took 4 atomic clocks, the most precise ones in existence, and placed them on commercial airplanes. They flew twice around the world, once eastward, with the Earth's rotation, and once westward, against the rotation. Meanwhile, identical clocks remained stationary at an observatory. When the planes landed, they compared the clocks, and the result was exactly what Einstein's relativity predicted. The clocks that flew east had fallen behind compared to the clocks on the ground. The ones that flew west had moved ahead. The difference was tiny, billionths of a second, but it was real and measurable. The clocks weren't malfunctioning. Real time, not just the measurement of time, had passed at different speeds for them. The pilot of the plane, in a very literal sense, aged a bit less than the people on the ground. His biology was slightly slower. His heart beat fewer times. Now let's scale this up. Replace the plane with a spaceship traveling at 90% of the speed of light. Suddenly, billionths of a second turn into years, decades. This leads us to the famous twin paradox. Imagine 2 identical twin brothers. One of them, whom we'll call the traveler, enters a ship and travels to a nearby star at an extremely high speed and then returns. The other, the earthbound, stays on Earth waiting. When the traveler's ship lands, what happens? According to relativity, the traveler is significantly younger. If 20 years have passed for the earthbound, only 5 might have passed for the traveler. He returns home to find his brother with grey hair, while he himself is still young. This seems to violate logic. Many argue that, from the traveler's point of view, it was the Earth that moved away at high speed. So, shouldn't the earthbound be the younger one? Shouldn't relativity be symmetrical? Newman analyzed the movement vectors of the entire system, and the answer lies in one word: acceleration. The earthbound remained in a state of constant motion without accelerating. The traveler, on the other hand, needed to accelerate to depart, brake to arrive at the star, turn around, accelerate again to return, and brake to land. He felt the forces of acceleration. It is this break in symmetry that determines who ages less. The twin who accelerates is the one who experiences less time. There is no doubt this would happen. It is proven physics. And this discovery has a consequence that fundamentally changes our perception of reality. If time is relative, if it can pass at different rhythms for different observers, then the idea of a universal now ceases to make sense. Think about this carefully. If you are on Earth and I am in a fast ship, our clocks mark time differently. This implies that there is no moment that is present for both of us at the same time. Your now and my now are different. If we are far enough apart and moving in different ways, what I experience as my present could be something that for you is already the past, or something that is still the future. If there is no universal present, the division between past, present, and future is not absolute. It is subjective. It depends on who is observing. This led some physicists, including Einstein himself, to a radical conclusion that sounds like philosophy but arises directly from mathematics, the idea of the block universe. The theory says that the past, present, and future all exist simultaneously. Time does not flow. It simply is, like a dimension of space. Just as north and south coexist, the past and the future also coexist. Everything that has ever happened still exists somewhere in time. Everything that is going to happen is already there. The universe would be a four-dimensional block where all moments are frozen and equally real. Our consciousness is what moves through this block, experiencing one moment after another, creating the illusion that time is passing, which leads us to an inevitable question. If the future already exists, recorded in the block, are our choices real, or are we just discovering a script that has already been written? The idea of the block universe places us before one of the oldest debates in philosophy, free will. If your future already exists as real as your past, in what sense are you deciding what you're going to have for dinner tomorrow? Some physicists and philosophers argue that free will is an illusion. We are like characters in a movie that has already been recorded. The complete story from beginning to end already exists, but we live it scene by scene, believing our choices are creating the future, when in fact we are just acting out a predefined role. Others argue that even if the future exists, our choices are the cause that determines it. It is a puzzle that science has not yet solved, but there is something the block universe doesn't explain well. Something so obvious in our daily lives that we forget it is one of the greatest mysteries in physics. Time has a direction. The past and the future are radically different. You remember the past but not the future. Eggs break, but they don't unbreak. Hot coffee cools down, but cold coffee doesn't heat itself up. Things wear out, age, and fall apart. Everything seems to move in a single direction, from past to future, from order to chaos. We call this the arrow of time. The strange thing is that the fundamental laws of physics don't care about this direction. The equations of Newton, Einstein, and quantum mechanics all work perfectly well both forward and backward in time. There is nothing in them that says time needs to flow in a specific direction. So, where does this arrow come from? The answer lies in a concept called entropy. When analyzing data from thermodynamics, which is a measure of the degree of disorder in a system, a whole egg is an ordered system of low entropy. A broken egg on the floor is a disordered system of high entropy. The second law of thermodynamics says that the total entropy of an isolated system, like the universe, always increases. Things move naturally from order to disorder, simply because there are many more ways to be disordered than to be ordered. If you shuffle a deck of cards, the chance of it remaining perfectly ordered is almost zero. There are trillions of disordered combinations, but only one ordered one. The universe moves toward chaos because chaos is statistically overwhelmingly more likely. The true mystery isn't why entropy increases, but why it was so low in the past. why the universe began in such an incredible state of order. The Big Bang was an event of extremely low entropy, with all the energy of the universe concentrated in one point. Since then, for nearly 14 billion years, the universe has been messing itself up. And it is this process that creates the passage of time we feel. This leads us to the question that has fascinated humanity for centuries. If the laws of physics are symmetrical, if time can dilate and almost stop, could it also go backward? Would it be possible to travel to the past? Mathematically, Einstein's equations of relativity do not prohibit this. There are theoretical solutions called closed time-like curves that would allow travel to the past, but they would require extreme conditions, such as the existence of wormholes held open by matter with negative energy, something that probably doesn't exist. And even if it were possible, we would face logical paradoxes that seem insoluble. The most famous is the grandfather paradox. You travel to the past and prevent your grandparents from meeting. If they never met, you were never born. But if you were never born, how could you travel to the past to stop them? It is an impossible loop. Some physicists, like Stephen Hawking, believe that the laws of physics must have some protection mechanism to prevent travel to the past and protect causality. Others suggest that if you traveled to the past, you couldn't change anything, because whatever you did would have already happened. And there is still the theory of multiple universes, where by changing the past, you would simply create a new timeline. We don't have the answer. Time remains the most mysterious element we know. But if time is so flexible, what about space? If relativity united the two, then space also must not be what it seems. Gravity, that force that keeps us pinned to the ground, might not be a force at all. Perhaps it is something much stranger, a warp in the very fabric of reality. Let's start with a fact that has probably never crossed your mind. At this very moment, while you listen to this, you are falling. There is no firm ground in the universe. The Earth is in free fall around the Sun. The Sun is falling toward the center of our galaxy, and our galaxy is being pulled toward others. Everything in the universe is in a permanent state of fall, and the reason for this is that gravity is not a force. Since childhood, we've learned that gravity is a force that pulls. Newton described it that way. The Earth pulls the apple, the Sun pulls the Earth. But Einstein, after 10 years of a mental effort that nearly consumed him, reached a deeper and stranger conclusion. Gravity is the consequence of the curvature of space-time. Imagine a sheet of rubber, stretched and perfectly flat. That is empty space-time. Now place a heavy bowling ball in the center. The sheet curves. It sinks under the weight. If you roll a marble across the sheet, it won't follow a straight line. Its trajectory will be diverted by the curvature caused by the bowling ball. It might even enter orbit around it, not because the bowling ball is pulling it with some mysterious force, but because the marble is simply following the straightest possible path on a curved surface. That is exactly what matter does to space-time. The Sun doesn't pull the Earth. The Sun, being massive, warps the fabric of space-time around it. And the Earth, in trying to move in a straight line through this curved space, ends up revolving in orbit. The apple falls on your head because the Earth's mass created a valley in space-time, and the apple is simply rolling to the bottom of that valley. There is no force, only geometry. The proof of this lies in what you feel, or rather what you don't feel. You don't feel gravity. When an astronaut floats in the space station, they aren't free from gravity. Gravity up there is almost as strong as it is here on the surface. What happens is that they are in free fall. The station is falling and they are falling along with it. And in free fall, you don't feel weight. What you feel as weight right now isn't gravity pulling you down. It's the floor or the chair pushing you up, preventing you from following your natural path of falling. And if gravity warps space, it also warps time. Where gravity is stronger, time passes more slowly. This means your head ages a fraction of a second faster than your feet, because your feet are closer to the Earth's center of mass. The difference is infinitesimal, but with atomic clocks, we can measure it. And this curvature of time leads us to the most extreme objects in the universe, black holes. A black hole is what remains when a very massive star dies and collapses under its own weight. Matter is crushed into a point so dense that the curvature of space-time becomes infinite. Nothing, not even light, can escape its attraction. That is why they are black. And as you approach one, time behaves in an unimaginable way. If you could stay safely near the edge of a black hole, the so-called event horizon, and look at the rest of the universe, you would see the future unfold at high speed. You would see stars being born and dying, galaxies colliding. Billions of years would pass out there, while only minutes would pass for you. In contrast, someone observing you from afar would see your image get slower and slower, redder and redder, until it froze forever at the edge of the abyss. At the event horizon, from an external point of view, time stops. And if you cross that boundary, for you, time would continue to pass normally as you fell toward the center, toward a point of infinite density that we call a singularity. What exists there, we do not know. It is the point where Einstein's equations break down. The conclusion of the theoretical models is the same. The laws of physics, as we know them, cease to make sense. The singularity is the end of the line for our knowledge. It is the edge of the map of the universe. We have made a long journey from Newton, wondering why the moon doesn't fall to a point in the universe where time itself ceases to exist. From the laws that govern our daily lives to the complete collapse of those same laws. What does this cosmic journey, from the familiar to the inconceivable, have to do with you? What can the dust of dead stars and the abyss of a black hole tell us about the meaning of being alive here and now? The answer to that question lies not in the distant future, but in a journey of nearly 14 billion years that brought us here. The universe began from nothing in an explosion of energy. The first particles formed hundreds of thousands of years later, then the first atoms, and then the first stars ignited, lighting up the darkness. They lived for millions of years, transforming hydrogen into heavier elements in their cores. When they died, they exploded, scattering those elements across the cosmos. New stars and planets formed from those debris. And on one of those planets, about 4 billion years ago, something we still don't fully understand happened. Life emerged, an unbroken chain of evolution, passing through extinctions and explosions of diversity that eventually led to an animal capable of looking at the sky and asking questions. You. This isn't a poetic story. It is your biography. The atoms in your body were forged in the hearts of stars that died long ago. The iron in your blood, which makes it red, was created in the agony of a massive star. The calcium in your bones, the oxygen you breathe. You are stardust, literally. And not only that, you are stardust that has become conscious. You are the universe observing itself. Matter that arose in the Big Bang evolved to the point of being able to question its own origin. And now think of everything we've discovered. Time stretches, space warps. Reality is much stranger and more wonderful than our intuition suggests. And we, this collection of atoms on a small planet, were able to understand this. The vastness of the universe doesn't make us insignificant. It makes us miraculous. Out of all the inert matter, all the silent void, a small fraction organized itself in such a way that it can feel awe, it can love, it can create. The universe didn't need to create consciousness, but it did. And you are the proof. This brings us back to the beginning, to the limit of the speed of light. We saw this barrier as a prison, a frustrating limit, but now we can see it another way. Numa examined the structure of causality, and the conclusion is clear. The speed of light limit is not a restriction, it is a guarantee. It is what protects the flow of time, what prevents effects from coming before causes. It is what creates and protects the existence of the now. The universe, with this fundamental law, is telling us something very simple. You cannot escape the present moment. There is no shortcut to the future, no return to the past. You have to live the experience moment by moment. And perhaps that isn't a condemnation, but rather the greatest gift of all. Because if you could jump to the future, if you could escape the present, you would lose the only thing that is real. You would lose the experience of being alive. If the block universe theory is correct, your life is a unique and eternal form in the fabric of space-time, a four-dimensional sculpture. Every moment you've lived still exists. Every joy, every pain, every person you've loved are not just memories. They are places in time that compose your story, a story that no one else has. What you do with your now matters. Every choice, every act of kindness, every time you choose connection over isolation, you are sculpting this permanent form. You don't need to discover the laws of the universe to leave your mark. You just need to live well, love well, and be present. In the end, the speed of light is not a limit on how fast we can go. It is a reminder that the now is all there is. The only place where life happens, the only time we have to feel, to learn, to fix, to love. The now is the only place where you can be alive. If you enjoyed this investigation, your subscription to the channel and any donation amount helps us expand the Numa project. We would love to read your reflection on the video's subject in the comments and your suggestion for the next topic to be covered. Tell us which city you are following us from. I thank you for your company until the end.